In this demonstration, we illustrate how an operator can teach a robot to assemble a diesel engine using voice commands and OpenDR tools. Since a real diesel engine was not available in Delft, we created a similar setup using 3D printed components. These parts mimic the bolts and the top case of an actual diesel engine. In this setup, the operator teaches the robot to assemble the engine using casual speech commands and RGBD images of the assembly area. The robot uses this multimodal input consisting of language commands and visual data to determine the correct actions. For instance, if the operator says, "Put the bolts in the outer ring," the robot then knows to move the bolts from their holder to the holes in the engine's outer ring. At the beginning, the robot lacks this understanding. However, through an interactive training phase, where the operator shows how the task is done, the robot gradually learns. Eventually, it gains the ability to perform the assembly autonomously. One of the key challenges in this task is the use of unstructured speech commands. These commands can vary in phrasing while conveying the same intent as those used during training. Additionally, the robot must adapt to variations in the setup, such as different orientations of the engine each time. Lastly, although providing demonstrations to the robot is crucial for its learning, it can be a time-consuming task for the operator. Our goal is to reduce the need for extensive demonstrations, while ensuring that the robot operates safely and autonomously with minimal human intervention. To minimize the need for real-world demonstrations, we initially train the robot using synthetic demonstrations created in a simulator. Usually, constructing a simulation pipeline that mirrors the real-world setup is hard work. However, the Luijkx tool from OpenDR streamlines this process. It allows us to use the same software pipeline for both the simulation and real-world applications, avoiding redundant work. Additionally, this approach enables us to thoroughly test a significant portion of the pipeline in the simulation. This helps in reducing unforeseen implementation errors, ensuring smoother real-world operation. After the offline pre-training phase, we transition the system in Luijkx from simulation to the real-world setup with 2 lines of code.
Pick the blue bolt and put it in the right tube.
This allows us to test the previously demonstrated commands directly. Remarkably, we observe that the robot is sometimes capable of executing these commands successfully in the real world, even without the need for additional real-world demonstrations. Despite the pre-training, there can be unforeseen scenarios or changes in settings. For instance, the robot might encounter a new orientation of the engine, as demonstrated here in this example, leading to potential errors in pick and place locations. In such cases, the partner tool serves as a safety net. It evaluates the robot's confidence in its proposed pick and place actions. If the robot is uncertain, partner proactively requests a demonstration from the operator, enhancing the accuracy and safety of the operation. After observing enough demonstrations, the robot can independently assemble the engine in different configurations, responding to informal spoken instructions.
Hey robot, please put the red thing in the middle tube. Could you pick the yellow fastener and put it in the left tube? The blue one should be placed in the right tube.
In this demonstration, we showcased a robot learning to assemble a diesel engine using OpenDR tools, including Luijkx, Partner, and the speech recognition tool. Luijkx facilitated the transition from simulated to real-world environments, reducing the need for extensive operator demonstrations. The partner tool provided a safety mechanism, requesting operator input when the robot encountered uncertainties like new engine orientations, demonstrating the practical application of these tools in robotic assembly.